Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. And what you're about to see is a pre-recorded training session we did over in the United States. But be assured that a lot of the material that we cover is really applicable to any automotive application. So just be aware that yes, it is a lot of North American vehicles, but they will apply a lot of the same principles apply over in the UK as well. Now, if you do have any questions, if you're watching this during the premiere, you can just leave it in the chat. We'll be monitoring live chat. If you're watching this after the premiere, then just feel free to leave a comment underneath the video and we'll get to those as we can as well. So my name is Jason Gabrenas. I'm one of Snap-on's diagnostic technical trainers. I've been in the training department since 2013, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep at Snap-on, so I had 30 different franchisees I worked with, as well as the shops that they serviced in order to help everyone get the most out of their diagnostic needs. Then before I did that, it was 8 years at Subaru, so I worked in a dealership, and over time, I guess, just became the default diag guy in the shop. So I always ended up having the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that would come into my day. Then before that, bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So enough about me. Let's talk about what we're going to talk about tonight. So we are calling this Data Bus Testing and Diagnosis Part 2, the sequel. So if you were with us last week, we talked about some of the data buses on vehicles. And this week, we're just going to dive straight in a little bit further with our two-wire buses. So as I said, last week, we talked about our low-speed network. So our J1850 variable pulse width and pulse width modulated signals. Our K-line bus, our LIN bus, which is a different type of communication network. And then we also had CAN bus we talked a little bit about. So today, we're going to start with a little recap on CAN and a little recap on how networks all work and how we're going to test them. And then we're going to dive into, as I said, those two-wire networks such as CAN, FlexRay, MOST, and then a little bit on Ethernet as well, or you might hear it called Diagnostics over IP or DOIP. That's one of the newer technologies out there. So to recap, Ethernet, or actually any networks, sorry, I still had Ethernet on my brain there. So any diagnostic networks that are out there, or any networks really, not necessarily even on a vehicle, operate off of voltage differential. We have our data packets, our ones and zeros that go back and forth between the computers that are communicating on the network. So depending on what the spec is for that type of network or what the manufacturer decided they wanted that spec to be, could vary. We want to see a certain voltage difference between the high side and the low side. So here's an example of a LIN bus. It's a single wire bus, and it is designed to have a 12-volt differential between that high and that low. So if we look on the high side, that is battery voltage or system voltage, right? So we're seeing 13.35 volts at that point right there. And then it is a constant high side, and then it pulls down to ground. So in this case, we see 0.91 volts down closer to the ground side. Now that is almost a full volt. Well, we see the difference between the two, our delta difference over here, is 12.44 volts. So that is within about half a volt of 12 volts. So we're right in the range of where we need to be. Around about 12 volts plus or give or take, about half a volt or so is a good signaling range for that. Anywhere outside of that, too high, too low, the computer might consider it just invalid data and decide not to use it. All right, so we want to make sure, depending on our network, what the voltages we're looking at. And then how are we going to test the networks? Well, many of them, at least with the communication with the scan tool type networks we're talking about, the easiest place to access that is at the diagnostic connector underneath the dash, right? And we talked about what all the wires were there. The key components we want to talk about tonight are going to be our grounds, right? So pins 4 and 5 are ground. Pin 16 is always power, as long as the fuse is good, right? So 4, 5, and 16. And then when it comes to CAN bus, which is going to be our first stop tonight, it's going to be pin 6 and 14 will be the main CAN bus on the vehicle. Now, some of these newer vehicles, when we get more and more and more modules on a vehicle, we need to have more and more different types of networks on the vehicle. So you may see other pins on this occupied by a CAN bus. Now you could have a couple other wires. I know GMs, for example, they've started about 2010 or so, splitting them off into different portions of the diagnostic connector depending on where the bus is. So you really need to make sure you read through a wiring diagram very well as well. And we'll talk about that a little bit later when we go live on the tool. We'll talk about going through a wiring diagram and kind of looking at how it works. So at least for this purpose, we're going to be mainly on pin 6 and 14 for CAN bus and most vehicle communications for that. Now, how am I going to access that? Well, we don't want a front probe. We don't want to push in to those pins on the DLC, right? Because that could cause a communication issue in and of itself if we make those pins break. Usually it's pretty hard to get behind those pins as well because they put that diagnostic connector somewhere under the dash, which isn't always the easiest thing to get to. So sometimes it's hard to get to the back. So easiest way to do this, non-intrusively, would be to use some sort of a DLC breakout box. This is our Blue Point branded one we have here. And that has a cable that comes off about a couple feet long, and it has a DLC plug on it. So you plug it into your diagnostic connector. There's a plug on the other end for your scan tool. So you can hook up your scan tool, communicate with the vehicle, all while monitoring the signals using the breakout box, right? So I have 16 different banana jacks, one for each of the pins on the DLC, right? And that allows me to get in there and monitor the signals without having to damage the connector or get in there. So CAN, quick recap. So high-speed CAN consists of 2 twisted wires with a transmission rate of between 100 to about 500 kilobits per second. And that's for standard CAN. When you get down to about the 100 kilobits per second, you're talking maybe a mid-speed CAN. When you get closer to the 500 kilobits, it's more of a high-speed CAN. And then there are newer versions of CAN that can get up to 1 megabit per second, right? So that's like 1 megabyte per second if you think about it that way. And CAN uses a 2 to 2.5 volt differential. If we were to look at the signals, we should see about 2 to 2.5 volts between the high and the low side. And once again, we'll talk a little bit more about that as we go on. One signal circuit is CAN high. The other one is identified as CAN low. So pin 6 would be our high side. Pin 14 will be our low side if we're looking at the diagnostic connector. And then at the end of each of the data bus lines, there's a 120 ohm termination resistor between the high and the low side circuits. And that acts as, let's call it a stop sign. All right, so here is the end of the line for my information. It just stops right there. We'll stop at that stop sign, the 120 ohm termination resistor. So here's just a simplified drawing of a CAN bus here. So we have our CAN high and we have CAN low, termination resistors on either end. More often than not, that termination resistor will be inside one of the control modules. So inside the ECM, TCM, BCM, what have you. About the only way you are going to test any network on a vehicle is you're going to need to use a scope because it is that voltage differential and is a higher speed than a meter, like a digital voltmeter, would be able to react to. But the only thing you can test with a multimeter on this would be checking the ohms reading of the line, right? So you could put one side of your meter into 6 and one side of your meter into 14 and see what the reading is, and it should be round about 60 ohms. Now, why 60 ohms? Well, if both ends of the line are 120 ohms on both sides, and we have 2 lines, we take that value and divide it by 2 because it gives us an average between the two. So we should see 60 ohms, give or take a couple ohms on either side, if we're going to measure the ohm reading. Can't really do a voltage reading on it when it's active, right? So really the only way to diagnose networks is with a scope. So with CAN bus, it's also modular, right? So we can have many modules on the bus, and we can add as many as we wish up to I guess there is a certain threshold that we can have before we start getting congestion on the network. But if we want more modules on there, we can just add more modules on there, and you will see communication. I know on some vehicles, you may have maybe an optional equipment package that is not installed on a vehicle. So they'll not have the module hooked up to the CAN, but they'll have a 120 ohm resistor plugged into the plug there. And then that is just the end of the line for that plug, right? I know on Subaru, we had a dealer installed shock sensor for the alarm. You would unplug the resistor, you plug in the piece, and then it just powers up, and there you go, off and running, talking on the CAN. You can even take the modules away and have just one module on there, and then you could still communicate with it using the scan tool, right? So it still will offer communication over that CAN bus, even if it's just one module on the bus. It'll still be transmitting information. So if we were to look at a high-speed CAN signal, we see that right here. We have our CAN high or CAN low. We have our idle state, which is this flat line in the middle, and then we have our data packets, which are all of these square looking pieces on the screen as well. So as I said, this is a little bit of a recap of what we talked about last week, but not everybody was here last week, right? So we just want to kind of give you that recap overview, because the basic premise of what we're trying to do here is going to carry across most of our 2-wire networks that we're going to talk about further in the presentation. So with CAN was great and all, and it's a 14, well, it's actually older than that. It was made in the 90s, but really it was standardized 2006. That is a 14-year-old standard anyways on a vehicle. And as vehicles get more and more complex, we have more and more modules. And as I said, we may have more and more networks on the vehicle. And CAN really has a limit at a certain point with how many modules can be on a network before we have data collisions and congestion on the network because of how CAN works. So the manufacturers, some of them got together and said, hey, we need a better standard here. So they talked to some engineers and they came up with the FlexRay standard. So FlexRay operates very similarly to a CAN bus, right? It is a 2 twisted wires. It has a transmission rate, though, of up to 10 megabits per second. So that is 10 times faster than the highest speed CAN bus, and it is 20 times faster than a normal 500 kilobit CAN bus high speed. Also on the signal, it uses a 1-volt differential, around about 1 volt on between your top and your bottom. So it's much less of a distance to travel. So it gives you that increased speed as well. One signal circuit is signal high. The other signal circuit is identified as signal low. Boy, that sounds an awful lot like CAN, right? The other thing with FlexRay is, depending on the manufacturer, if they wish, they can also have redundancy built in. So they can have 2 pairs of wires carrying the same signal. So in case one pair of wires goes down, we can use the other pair of wires to still communicate. It's used for very high speed vehicle driving down the road sort of communication, drive by wire or what have you. And I need to press my throttle. The signal needs to get to the ECM. The ECM needs to make its adjustments and determinations and calculations and send that information out to the electronic throttle motor, all within less than a blink of an eye, because I don't want to have any input lag from my pedal. Right, so we need to have some sort of a high-speed network, and this works great in those types of applications. Many manufacturers use this. Now, at each end of the data bus in here is also, once again, very similar to CAN. It uses anywhere between an 80 to 100 ohm termination resistor between high and low. So I guess that must be more at manufacturer's discretion than just a standard, here's your 120 ohms for CAN. So here, if you were here earlier and you watched the video that I played at the very beginning, we saw a live FlexRay bus coming off of BMW. This is a screenshot off of that. So this is very similar, you'll see, to CAN. I have my middle of the inactive portion, and then I have my active portion with my data packets, right? So these are all the different data packets on the screen. Now, one thing I'd like to note here is between CAN and FlexRay, we can see the difference in the transmission speed just by looking at this. So we see when I'm on 100 microseconds time base here. So that is 100 millionths of a second from the 0 over here to the 100 over there. That's 100 millionths of a second occurring. Looks like one of those data packets, I don't know, 45 to 70. So that's what, 30, 35, 40 different, yeah, somewhere in there, 35 microseconds, right? So it's not very long, that data packet. Now, if we were to compare that to CAN, as we looked earlier, on that same 100 microseconds, I can't even fit an entire packet of CAN data, right? It's actually wider than what this screen is. It's more of like a 200 microsecond distance from front to back. So we can fit 3 of these FlexRay bus signals in the case of where we can put half of a CAN bus signal. So that is showing you your speed. So it's getting closer together. That means it's faster, right? So now we can see how it is considerably faster transmission speed. We can still pick it up with the scope, but it is faster than CAN. And that's really why they wanted to start using that, right? So it gives us that faster network. Then we have MOST. I included MOST in here. It's not really a diagnostics communication network, so to speak, but diagnostic information can travel through it. But it is made for media transport, right? So MOST stands for Media-Oriented Systems Transport. Many manufacturers use this type of network inside their vehicles. It is a dedicated high-speed multimedia streaming data bus independent from the CAN bus of the vehicle. So it's separated. You may have a gateway module to translate signals between them, but it is separated and it's used only for multimedia, so video, audio, and the like. So the most bus is configured in a physical hardwired loop with each device within the bus, sending and receiving data on an assigned address in a set order. So each part of the bus has its own, let's call it an IP address. It's not Ethernet, but we'll just say it has its own address on the network. And then each one goes in turn around this ring. Now the radio is the most master and monitors the bus for vehicle configuration, infotainment data messages, and errors on the bus. All right, so the radio is in control and everybody else talks through the radio. So here's just an example of a most bus on a vehicle. I think it's on a Cadillac. Now, some vehicle manufacturers use copper wire. Some manufacturers use fiber optics. There we go. That's the word I was looking for. So some can be copper, some can be fiber optics. Either way, you're probably not tapping into this network to test. You can, I guess. If it's copper, if it's fiber optics, you're not going to be able to see anything because it's just light transmitting, and then we have translators on either end. So you're really not going to be able to tell anything with that. But with the copper, you would be able to see signals, and it's similar to what we would see with CAN on the copper networks. But the radio is the master, and then we see I have these arrows which show me the direction of travel. So it comes out of the radio and goes to the audio amplifier. Then from the amplifier, it goes to the instrument cluster. From the cluster, it goes to the media disc player, because we all have separate disc players now, not attached to the radio. Remember how you used to be able to just pull the radio out and replace it with a new one? Yeah, not so much anymore. So we have the media disc player, and then it goes out to the human-machine interface control module, which is a really fancy way of calling that a touchscreen. So that's what it is. All right, where the human and machine interface, that's our touchscreen. And then back to the radio. All right, so that is a hardwired loop, physical hardwired loop, where each of these talks on its own turn going through the network. Now let's talk about Ethernet. Ethernet's the new kid on the block. It's only been in the last 5-6 years we really started seeing this coming on the scene in vehicles. I'm sure there were some other manufacturers before that who were using it, but it wasn't nearly as widespread as it is starting to become. Now, automotive Ethernet consists of 2 twisted wires, could be multiple pairs of twisted wires, with a transmission rate up to 100 megabits per second. So that is 10 times faster than flex rate. This is very fast information. Now, when it comes to Ethernet, Ethernet can have 100 megabit or it can have gigabit, right? So we have megabit and gigabit. Gigabit is even faster than that. It's about 10 times faster. Most automotive manufacturers have decided to go with the 100 megabit per second because it's less complex than gigabit. Some manufacturers, we'll see in a second, have decided to go with gigabit Ethernet, but as far as the majority that are out there, they went with this 100 megabit per second. Ethernet is a completely different animal when you want to look at the signal. And I'll tell you what, you probably aren't going to be cutting into an Ethernet cable or tapping into an Ethernet cable to measure that too. Oftentimes there is specialized equipment needed. And then even when you look at the signal, which I'll show you in a second, I don't want to say there's no rhyme or reason to it, but it's really hard to pull out a pattern and what's good and what's not good based on how the signal structure is set up. Right, so they use what they call a PAM3 voltage signal. So PAM stands for pulse amplitude modulation. So it changes the height of the pulse, the amplitude. And that is a signal with 3 different voltage levels. That's where the 3 in PAM3 comes from. When you get to gigabit and more complex networks, you could have a PAM5 network where it has 5 different voltage signals. So what am I talking about by 3 different voltage signals? Here's an example of an Ethernet signal taken on a specialized lab scope used for network diagnostics in like data centers, right? So they use a lot of Ethernet there in the computer world. So what it is we see it's about a volt at the top, it's about a volt at the bottom is what our range is for the data transmission, right? So about a volt on either side. There's 0 volts in the middle. So it's actually more of like an AC type signal, goes both on above and below 0 volts. Depending on how the system designer wanted to set it up, they will have breakpoints in the signal. So I just represented these by these red lines, which are right about 500 millivolts positive, and then negative 500 millivolts here. Any signal that goes below that break line, so all of these signals here are considered a -1 signal. Anything in between the two are considered transmitting a 0. And then anything above the high side is going to be considered a +1 signal. So we have both +1 and -1 and 0. So we get all three of those could be in here. Now, as you see, there's not a lot you can tell by looking at that pattern, right? So when it comes to diagnosing Ethernet, I'm thinking you're going to be using more of the codes and flow charts from the manufacturer who set this up. Just based on it seems to me there's not a lot of consistencies. Whatever's higher than whatever they decided it to be, right? And whatever's in between whatever they decided that voltage range can be, and it can vary. All right, so there is our Ethernet signaling, and we're also looking at a very short amount of time on the screen. We're in the billionths of a second there. So specialized equipment is needed to diagnose it, at least to see the voltages, right? Here's an example of an Ethernet equipped car that we found. So this is on a 2018 Volvo XC60. And I wanted to see, from the diagnostic connector, because that's where I'm going to be plugging in my scan tool, right? And that's where I might have a communication issue. What do we see? How do we communicate with the car? Because I know you also have to communicate with this car via Ethernet or diagnostics over IP. And come to find out, if we look at the wiring diagram here, this is a wiring diagram from Volvo. Pin 6 and 14 are my CAN bus, and those go back over to this module over here and this module down here. So this is a CAN communication. This module over here uses FlexRay CAN and LIN, so it does not use Ethernet in here either. And then we also have some sub buses that go back to the connector as well. So they have multiple CAN buses on this vehicle. All Ethernet on this car is internal, inside. So when we communicate with it, we have to go through the gateway module. The gateway then translates it to Ethernet for the rest of the engine, the transmission, the higher speed information that we need inside the vehicle. And I've found that's the case in many vehicles, not all vehicles, but many vehicles. It's CAN or some other sort of more common protocol until it gets into the vehicle, and then it's Ethernet internally. Another interesting thing I saw when I was there investigating these Volvos, I was at a dealership, and while I was waiting to hook up to one of the vehicles, I was talking to the lead tech there, and he said, "Oh yeah, I have these three cars hooked up, and they're all getting reflashed right now." As a matter of course, for Volvo, whenever a car comes in for maintenance or what have you, they will check and just automatically update the software for you. And apparently there's quite a few software updates out there for just the little things, right? And they were updating it wirelessly over the car's Wi-Fi. So they have Wi-Fi in the shop, very powerful Wi-Fi. It's hooked to a hard line to the internet, but they flash it from just as a desktop PC, and they had 3 different cards they could switch back and forth, and they were able to program it, flash it over the air. They just had a battery maintainer on the battery, but they were able to flash the vehicle over the air. They also have when the Wi-Fi doesn't work, he said, here's the cable we use to plug in there, and it's an Ethernet cable there as well. So I think in some cases they can have Ethernet right at the port as well, but they do everything pretty much Wi-Fi. They diagnose the vehicle wirelessly. All right. So when we hooked up to this car at the CAN bus, we see it does look just like any other CAN bus, because this was not, like I said, it's Ethernet internally, CAN bus externally. So it looks just like standard CAN bus right there, right? So you have our 2.5 volts in the middle. We have our 3.5 volts or so on the high end, 1.5 on the low end. And I was able to get that from pin 6 and 14 right at the DLC. Now, in order to communicate with the car internally, since the computer and everything is communicating using Ethernet, you do need specialized equipment if you're going to use a scan tool. I'm not sure about other scan tools, but I know for a fact what Snap-on does. And we support the vehicles listed on the left-hand side. So we have the Jaguar I-Pace 2019 model year, Land Rover 2018 and newer, Discovery, Range Rover Sport, Range Rover Velar, and then all those Volvo models down the bottom. Started about 2016 when they started putting Ethernet in the cars on forward. So there are 2 ways to go about this, or actually 3 ways to go about this. If you have a Triton, an Apollo D8, a Modus Edge, a Modus Ultra, a Solus Legend, a Solus Edge, a Solus Ethos Edge, and a P1000, you need this specialized cable that looks like it maybe like a snake that swallowed a rat or something like that. It's got a big bulge in the middle, and that is where all of the translation takes place between, I guess, regular communications and the Ethernet network. If you have a Solus Legend, it actually comes with it in the box. All right, all the other tools, you'd have to grab it separate. And if you have an Apollo D9, the newest Apollo D9, it actually has the Ethernet translation built into the board on the tool. So you don't need a specialized cable, but it does have its own cable that has a keyway on the end. And then we also have, if you have a wireless tool, Zeus or Veris Edge, you can use the what they call the S7 wireless module. It's a little bit bigger than the one that came with the Zeus, and it's a lot smaller than the one that came with the Veris Edge. The Veris Edge was the S4, is the big one with the cable. So both those tools are able to communicate with those vehicles over that wireless module. So if you're interested, or if you have the need to communicate with these vehicles, definitely talk to your Snap-on rep about getting that. And also just last year, and this is actually current events at this point, but announced in May 20th of 2019, GM said they are going to Ethernet protocol as well. So it was introduced in the 2020 Cadillac CT5 and the 2020 Corvette. So that new fancy mid-engine Corvette they had come out, that has Ethernet on it as well. They're going to filter it in through the product line over the next few years, and by 2023 model year, almost all GMs will have this in there. Capable of processing 4.5 terabytes of data an hour. That is a five times increase over where they're at right now, which is what they call Global A network. Also utilizes Ethernet communication internally. So once again, internally in between the modules, and they go up to 10 gigabytes per second. So they went with gigabit Ethernet. Remember how I said a couple manufacturers decided to go with gigabit? That's GM's way. So they decided they'd go with 10 gigabits per second. And it will offer, once again, that over-the-air updates very much like Volvo does. But I think the way they're going to do it is over your home network or your car's own network if it has one. Much like Tesla does. Tesla does that already, where you can download updates to the car, over the air. All right, so that is here. It's coming. It's becoming more prevalent, should I say. But it is here now. Ethernet is here now. And it's just something I wanted you guys to be aware of, that it is coming down the pike, and it is something we're going to have to deal with. But as I said, to diagnose it, more than likely, you're going to be using codes and flowcharts, not really necessarily testing equipment at that point. So let's go live here and talk about a few other things network related on our tool. All right, I see a couple questions come through. I will definitely get to those in a few minutes when we get to that point. So I'm going to pull up a 2015 BMW X5. Where is that? Oops, X5, X-Drive 35i. There we go. I'll pull this up. I want to talk wiring diagrams here for a second. Oh, X4, sure. I clicked the wrong one, but that's okay. It should still have the same information. All right, so I'm going to pull up wiring diagrams here out of Shopkey, and I want to look at my computer data lines, because that is where all my network stuff lives. All right, so here's my network, 4 panels for the network, all right? And here's the diagnostic plug. So let me open this up a little more. Here's a diagnostic plug. So most of the networks on this vehicle, you'll be able to tap in through the diagnostic plug. There's some internal ones you won't be able to. But we'll see, pin 3, that looks like an Ethernet data line, actually. And then we have 6 and 14, which are CAN bus, 11 and 13, and so on and so forth. So most of those pins on that diagnostic connector at this point are taking up network communication duty. We look over here, this is the, what module is this over here? This is the, get down to the bottom here. So that's the central gateway, right? So that's who translates all of the different signals between all the different modules. So you see you have Ethernet, 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 KCAN, PTCAN, Ethernet, KCAN, PTCAN, diagnosis bus, terminal 30F, which is power, Ethernet data line, ground, Ethernet data line, more FlexRay up here. So we have multiple networks all merge into this one box on the vehicle, right? So we need to be able to trace that back. So let's say I wanted to look at, let's see. So there's FlexRay there. Looks like there's lots of individual FlexRays, right? So it's mostly pink and green on this vehicle. Goes to the different modules. Can go across. And we can see how there are multiple modules on this vehicle, all with different variable networks. Some are single wire, most are dual wire at this point because it's just a lot faster. All right, let's see through here. So digital motor electronics, so that is the PCM. So as far as what's connected to the PCM, my camera has a line. Let's see, PCM goes down to parking brake control module, crash safety control module, gear selector switch, fuel pump control module, transmission,
goes off the page over there. All right, and it goes over to the gateway module. Now you'll notice not everything in the engine goes to the gateway module, though. It goes across, and then it goes to the gateway module to then translate that signal for us out to the other various modules on the vehicle. Right, so it's only 1, 2, 3 wires that go from the CAN bus on the computer back to that gateway module. So the gateway module in this vehicle is very, very important in order to be able to check our networks. It may give us an access point too, depending on how the connectors are set up. It may give us a good access point inside the car on how to test that. Let's also look inside guided component tests, right? So we'll pull up the same vehicle. Let's see what we get on my engine. We have CAN bus tests and fluctuate bus tests as well. So if you wanted to go into CAN bus tests, tells us all about CAN bus, tells us we want to connect to the computer in order to check the CAN bus on this particular vehicle. If we go to a signature test, it's going to tell us exactly what it should look like, right, and what our voltages should be. If I hit view meter, it'll actually open it up and it'll show us the information on the screen as well. So there's a sample CAN bus pattern. I know we looked at this last week, but there is a sample CAN bus pattern there. So 200 to 350, that's about 150 microseconds, 150 millionths of a second. Also note, I know I mentioned it before, but I'll mention it again on many CAN buses, not all CAN buses, but on some CAN buses, you may see this extra large bit here at the end, and that is a what they call an acknowledgement bit or an ACK bit. Therefore, it's an acknowledgement that it sent the data and that the receiving module received the data. So you will see an extra large spike at the end there as well. All right, and then for flex array bus, right, we can go in there. It's going to tell us all about the bus. Doing this, the wiring harness size is greatly reduced, higher speed, better connectivity. No bus communication at 2.5 volts, just like CAN, and then it goes up to about 3 volts and down to about 2 volts. So that is about a 1 volt differential there. And then there is what my typical FlexRay data packet looks like there as well. So we'd be able to hook that up, hit view meter. I don't have an example to connect to for FlexRay, but we could see that in there as well. All right, so many vehicle-specific options for that. Also, checking our wiring diagrams. Very, very important to be able to test and check the wiring diagrams as well. I think that's really, really key, especially when it comes to these more complex vehicles today.
And with that, that is our time here today. So make sure you tune in for new diagnostic content every week. We will be premiering a new video every Wednesday at 7 p.m. UK time. So make sure you check it out on the YouTube channel. If you're watching, well, of course, you would be watching this on YouTube, but make sure you subscribe, thumbs up, ring the little notification bell so you know anytime we post new content. And it's youtube.com/SnapOnDiagnosticsUK. With that, time for questions. If you have any questions, just feel free. Once again, if you're watching this on a premiere, just leave it in the live chat and we'll answer those. Otherwise, leave a comment under the video and we will get to those as we monitor those comments as well. So I'd like to thank you for taking a little bit of time out of your day to learning a little bit more about how you might be able to be more efficient at diagnosing vehicles using some of the information that we've given you today. Hopefully, we'll see you next week. Hopefully, you can watch and see you on any of our other videos. Have a good week. Have a good night and take care.